of gate driver circuit for power electronics converters. Okay, that we are going to discuss. Uh, So why it is important? Okay, basically you know that I hope you are all aware about the different circuits of the power electronics converter. Suppose you know that power circuit, control circuit. Okay, so what is the purpose of the what is the purpose of the power circuit? To transform the power from source side to load side, or load side to source side, means vice versa application. But who will decide? Okay, but who will decide to transform the power or transfer the power from one direction to another direction? Normally it is decided by the control idea. Okay, so that means it is normally decided by the structure of the controller and the operation of the controller. So how is it working? Okay, so based on that logic, based on the logic, the power can be transformed from one into another end. Okay, as simple as it. But how to control? Okay, normally that is decided by the logic, and that logic can be implemented by the gate driver circuit. Okay, so you know that basic idea of the control systems. Okay, or the in my measurement class I have also discussed on it that how, suppose you are sensing one parameter, then what you are doing, you are comparing that parameters with some reference with some reference value. After that you can see the some error value can be generated. Okay, that error can be passing through that your compensator, okay, or the controller, and that error can be minimized by the controller, and you will get some control signal. And that control signal nature is almost very slowly varying. Okay, not very slowly varying, slowly varying. Okay, so you can say like that it's an almost approximated DC value. Now that DC value can be compared with some repeating sequence, or in it may be in triangular nature, or it may be in short-root in nature, whatever based on your requirement. Okay, and you can get the PWM. Okay, and that PWM can be fed to the solid state device. But thing is that you are getting the PWM. So if the PWM signal strength is sufficient enough to drive the solid state device or to drive the switch of the converter. Okay, so am I audible properly from your end?
Yes, sir.
Yes, sir.
Is there any background noise? Is there any background noise?
Little bit.
Yes, sir. Little bit.
Okay, just wait for a moment. I just switched off my fan of my office. Okay, just for one, just for a second. Okay, I'm just switching off that. Is it okay now? Hello?
Yes, sir.
Okay, okay. So that is very important thing. So based that signal strength. Okay, so what do you mean by the signal strength? Okay, so if you normally we know that the different set of converters are there. Sorry, different and types of solid state devices are available in our local market. Okay, so based on that requirement, we can pick them. Okay, suppose we are having MOSFET. Okay, MOSFET is very commonly used device in for that normally for fabrication purpose and laboratory small prototyping purpose, whatever we are fabricating. Okay, so normally we have taken the MOSFET. Okay, and we start fabrication. Okay, there are some reason why we are picking the MOSFET. Okay, basic reason is that MOSFET is quite cost efficient. Basically, the cost is nominal in the range of 50 to 100 rupees for our nominal users. For laboratory scale means whatever we are doing below 100 watt. Okay, so that is sufficient enough. But MOSFET has a problem having problem of non-minimum. Sorry. Problem of it's a sorry, not in problem. You can see it's a very high frequency switch. Okay, so you can say go up to 500 kilohertz. Okay, but so we have to design the gate driver such a manner so it can be provide up to 5000 sorry, up to 500 kilohertz range. Okay, so based on that you have to select it. Okay, but in MOSFET another problem is it's a voltage control device. Okay, but we are having also the same thing that we are talking about power MOSFET. The power BJT also be there. Okay, so MOSFET is a voltage control device, BJT is a current control device. Okay, but the current strength of the BJT is quite, it's required more. Okay, so same signal, okay, getting from the PWM or from the gate driver circuit is not eligible to drive that power BJT. Okay, what is the problem? The current strength. So what we need to do, we have to add some more for amplifying the current. Okay, we need to add some amplifier circuit. So suppose not exactly amplifier circuit, some configurations of that signal transistor. Suppose SL100. Okay, in totem pole configuration or Darlington configuration, whatever required for you, you have structured them, okay, and fabricated them and passing the signal through that combinations, and you can get that amplified response. Okay, and you can get that amplified response. That response can, or that signal, amplified signal, that signal can drive your your power BJT. Okay, but in case of MOSFET, what happened? It's not required. Basically, nominal current is required. For additionally, you have to use some 100 ohm, okay, or 100 to 500 ohm resistance, the series of that gate driver of the MOSFET. Okay, so you know that in case of when you are sending that pulse to that switching device, so normally we are giving the gate terminal. So if we are considering the MOSFET, so normally we are providing the pulse in between gate and source. Okay, that means source can be grounded. Okay, or you can say like that source can be directly connected to the ground terminals of your control circuit. But the problem is that you know that power electronics converters are working in megawatt range, sometimes high kilowatt range. Okay, that the versatility is more. It can be. Hello. Hello. Am I audible?
Yes,
Yes,
sir.
sir.
The versatility of that converter, that power electronics converters are huge, from quite fractional watt to up to megawatt range. Okay, suppose we are considering for the power circuit in megawatt range, but our control circuit we are using some op amp. Here I just showing you the circuit. Okay, so here we are using some op amp. Okay, so you know that 1, 2, 3 op amps are there. Okay, in a single TL084. So which batch we are using? TL084 batch are using. Okay, so one TL, you can also download that Texas Instrument IC. Okay, the data sheet. Okay, you can download the data sheet. So you can also understand the pin diagram. Okay, when we are using some IC, we have to know the pin diagrams. Okay, as well as the basic features. Okay, which what is the highest operating region. Okay, so we are designing a gate driver circuit for MOSFET. So which op amps can take up to 500 kilohertz range, that op amp need to be selected. So TL084 is a Texas Instrument op amp set of op amps. So one TL084 contain 4 op amps. Okay, so one op amp having has 3 length. Okay, and 2 biasing terminal, 3 terminal, 2 biasing terminal. Okay, so 1, 2, 3, 4 into 3, it is 12. Okay, so one is positive, means one plus VCC. Okay, means bias, positive bias voltage, another one is negative bias voltage. That is negative VCC. So total 14 length. Okay, so if it is more than that, so if there is any ground terminal, you can cross check it. Okay, so whatever the numbers of terminals are required for that one. Okay, so and selection of that op amp also been decided how much maximum kilohertz range it can be run. Okay, so it can be work, otherwise it will not work. Okay, and you know that the power circuit is in megawatt range, can be in megawatt range. Okay, but your control circuit, you know that what is your biasing voltage of the maximum volt. Okay, 18 to 18 volt. Now standard. Normally we are using 12 volt and 15 volt. That two are the very standard. So that op-amp can uplift that gate pulse that you are getting, that can be up to 15 volt. But it can handle, the power circuit can be handled in megawatt range. Okay, so what we need to do, we have to isolate the inputs. We have to isolate our converter. Sorry, we have to isolate our control circuit from the power circuit. So from where we are going to be isolate? Suppose you can realize, you can just realize the basic structure of the system. So we are giving some reference value. Okay, we are giving some reference value and tracking. Okay, so we are talking about closed loop system. Okay, we are giving some reference value and we are tracking the output. Okay, so what happened? That output is coming from your output of the converter. Okay, so that converter may be any rectifier, that can be any cycloconverter, inverter, whatever may be, what can be there. Okay, any kind of converter may be there, but their actual reference and that your actual reference means calculated reference, means what you want to desire, the desired value of the reference. Okay, and your actual reference is what you can measure. So every experiment, whatever from beginning, so all the experiment I am talking about, please prepare an observation table. Okay, where we are getting the different column. Okay, so one column is our calculated value. Okay, or you can say like that, that is our difference voltage. Okay, reference output voltage, and we are also collecting that measured value. Okay, measured output voltage. Okay, so both are there. Okay, so what we are doing, so both values, so and we are also find out that error signal. So that's the motivations. Okay, that kind of motivation is required for this type of study. Okay, so if that range is more, okay, that error is huge, so what happened? So your system is, error value more means what? Your system is going to be diverging, means normally it is stable operations. Now error is making more. So what will be the problem? Your system goes to instability. Okay, it goes to instability. So what you need to do, you have to minimize the error. So how to minimize the error? Okay, so suppose one of the switch is working. Suppose you are having one buck converter. Okay, so buck converter purpose is that output voltage you are making them less. Okay, so suppose you are changing some load. Okay, changing some load. So that load changing means in electrical point of view, what can I know? So that load stands for current. Okay, more load means system is drawing more current. Okay, so load less means system is not taking so that amount of current. Okay, so normally as per our as per our knowledge, both energy conversion of that energy, conservations of the energy. Okay, conservation of the energy means its overall energy should be fixed. So in another simplified mode, energy is an integrating factor of time. So both the cases, input energy is equals to output energy. So it's an integrating factor, means both the cases times are involved. So we can also say if the time can be constant, cannot be cancelled, means cannot be zero. Okay, can be constant, making them constant both the sides. So you can see the both input power and output power should be same. Now you are taking more load, means suppose in output side load is more means current is more. So power is fixed. So what happened? Voltage can be dropped. Okay, current is more means voltage can be dropped. Okay. So more load means voltage can be dropped. So you are giving that voltage reference. Now you can see your output voltage, whatever your required output voltage, that is dropping. I hope all of you realize the problem. What I am trying to say, I hope you are realizing the problem. If you face any difficulty, please ask me again. I will discuss. But try to realize the thing. Okay. So what happens? So your output voltage, rated output voltage goes down. So what happens? Your error will be more. Okay. System is trying to go to the instability. Okay. Then what you need to do? How to uplift that error? Sorry. How to uplift the drop voltage? Okay. So your turn on time of the switch should be more. Okay, so what should be your logic when you are designing the gate driver? Okay, so your error will be more, means your compensation voltage. Okay, that error normally passing through the compensator. That's the function of the controller, minimizing the error. Okay, so that's the function of the that's the purpose of the controller, minimizing the error. But problem is that how fast it is mitigating. Okay, how fast it is mitigating, that's the dynamics of the controller. Okay, so if the dynamics, it is very fast mitigating nature, so it's very good controller. Okay, that's why versatility of the controller is coming in the field. Okay, why different types of controllers are there? That's the basic reason, versatility of the controller. Okay, so this controller, suppose IMC control, internal model control, they are giving very fast response, meaning quick point. Chances for internal instability. Okay, so internal instability means in between. Okay, so in between there is a problem of that improper transfer function sometimes. Okay, so we have to normalize them. Different problems may be there, but their response is very fast. Okay, system is more robust. So your on time will be more, means converter will be working for the more duration of time. So automatically voltage will be high. So converter mode means that DC value. Okay, so slowly varying value. Okay, in standard rated condition, how in the rated condition, what kind of error value is coming, or sorry, what kind of control signal is coming from the compensator. Rated conditions, if the load is more, if the load is more conditions, what happened, that error will be more, the voltage signal value, okay, the control signal value also been more compared to a rated condition. So what happened, the shifting will be there. Okay, y-axis DC shifting, positive y-axis, positive y-axis DC shifting will be there for your rated conditions. So, and you know that your repeating sequence, that a triangular one. Okay, so plus minus, okay, both the side it is there. Okay, their height is fixed for the first condition as well as second condition. So it is try to reach the peak. Okay, try to reach the peak. Normally, if it is in middle of that one, reference conditions, okay, touching the middle of that one. So now as it's try to be 0. Now it is goes to shifting upper side. Okay, then what happened? As per the logic, you have to make the logic when that value is be more. So when that your triangular value, okay, the triangular value will be more than your control signal value, the converter should be turned on. Okay, so if you fix that condition, so automatically PWM of that converter gate driver is automatically increased. Okay, if you make them reverse condition, then what happen? Then it will be again thinner in nature, the PWM in according to a rated condition. So converter will be turned off quickly. So compared to your rated condition, so again goes for the instability. That's the reason. So you have to make the converter on time for the more durations. So automatically you can see that your converter will be turned on for the more duration. So output voltage will be more. If the output voltage will be more, so your actual voltage and your reference voltage. Okay, so that error will be less. If your output voltage will be more, error will be less. So all the thing will be gradually again stabilized. That's the purpose of the converter. Sorry, that's the purpose of the controller and the implementation of that circuit. Okay, so that happened in this condition. So we are talking about isolated and non-isolated. First, directly we are taking the response from your load value and then compare, and everything will be there. You can see the both the cases that ground are not isolated. So what will be the problem if ground are not isolated? For the very costly circuit in megawatt range, so circuit control circuit is most costly compared to your power circuit. Power circuit also costly as per the power level, but if you compare them in the power level, so control circuit also very costly. Okay, so costly equipment sometimes we have given. Basically, right now we are using digitally control system. So digitally control means digital processor will be there. Your laptop will be in the loop. That's why right now it is called. It is not called hardware experimental setup. It's not like that. It is called HIL, hardware in loop. So your converter will be there and it can be controlled by the digital processors. It may be your computer, it may be computer means it can the MATLAB installed in your computer, any other software can be installed in your computer, and through that you know that some interface integrations are required, interface is required. Okay, so how do you control it? Okay, everything can be decided by the digital processor. Okay, so you can understand the costly of that processor. Okay, and you are trying to run the converters, and that is so much costly compared to your digital, compared to your control unit. So any fault happened, so that may responsible for damaging of your control circuit. If both the cases ground are same, that we are talking about forcefully for giving the gate pulse to your MOSFET. So we are giving in case of MOSFET, it is gate drain source. Okay, for IGBT, it will be gate collector emitter. Okay, so IGBT means combinations of BJT and the MOSFET. So both the possibilities are there, but it cannot be operated up to 500 kilohertz range. IGBT, it's not possible. Okay, so some of the value, moderate value, it can be operated, but not so much high frequency. Okay, so what happened? You have to make the you need to separate the both the ground. Okay, how do make it separate? So in measurement subject, we gone through one chapter that is called sensor and transducers. Okay, so we are talking about tachogenerator. So tachogenerator can convert the electrical energy or RPM. You know that one RPM to that electrical energy. Okay, sorry, electrical value, some reference value, voltage. The similar kind of thing happened for Hall effect sensors. Normally we are using for the controllers. Okay, converters. So purpose of the Hall effect sensor, that magnetic, its electrical energy will get it through that magnetic field. Okay, so magnetic isolation is there. So but the sensor cost is very high, so it is around 5,000 rupees. Okay, but sometimes we are also designing some system whose cost is not in thousand. So okay, that cost may be in 100, 500 or 600 rupees. Okay, so in that case we cannot afford such costly device, so we can use some voltage divider circuit. Okay, so voltage divider circuit. So whatever sensing is there, okay, after that what happened? We are we are completing the sensing through that transducers. Okay, so any of the physical mode of signal, it can convert it to that electrical energy. Okay, that's why transducers are very famous in this domain. Then we will get the signal. That signal strength is not so much high, so you have to amplify it and scale it to comparable appropriate comparable region or comparable range of your reference value. After that you can only compare. Otherwise you can compare, but the results will be wrong. Enter calculations can be wrong. Okay, so we are comparing them. Then what happened? So how to get it if you are using digital processor? So first analog to digital ADC converters are required before entering to the computer. Then when if you want to process all those signal, now try to send the signal from your computer to the physical system. So how do you send it? Okay, so again you need to accommodate one digital to analog converter. Okay, DAC converter for accommodating all those things or converting all those things. So what you can see, then after going conversions, if you have MOSFET, so you can use some Smith trigger. Okay, and you will get that money. Smith trigger means any triple five timer. So you know that how to get what is the purpose of Smith trigger. Okay, so then you can get the PWM. That PWM can be compatible for this one, but for that isolated converter, so isolated ground conditions. Okay, I'm talking about right now for non-isolated. Okay, so for isolated conditions, what we need to do, as we are having the system, okay, but they are grounded, combined or clubbing with our power circuit. So that may reason for damaging our control circuit. So what we are doing? So we are isolating. So initially we are using we are using magnetic isolation through LEM sensor or transducer, and before after coming back from DAC, okay, digital to analog converter, then we are using some opto isolator. Okay, opto isolator, again there are different varieties of opto isolator, MCT2E. Okay, then Okay, so MCT2 and other types of for high frequency applications. Okay, so if it is more than 20 kilohertz application, so MCT2 is not able to give you the results. Okay, so we have to think for that more rated opto isolated. So it's create the optical isolation. So first isolation is done by the transducers or sensors from your input just after the output, and another isolation you can observe just getting the output from DAC to providing the pulse to your DL converter. Okay, so there another isolation is required. So that can be done by the opto isolator. After opto isolator, we are providing the 555 timer to drive the circuit. That's it. That's very basic thing. So here we can see three. So first we can see that circuit. Okay, so the purpose of that circuit is to generate the triangular waveform. Okay, so we are using here on R is there and C is there. There is a RC circuit. So that way responsible for generating some slope. Okay, so if you vary the value, so automatically the triangular waveform slope can be varied. Okay, then what happened? Then you can see that you can see 1, 2, 3. So first 1, 2, 3. Sorry, 1, 2, 3. So first I see in TL084 I see first one can be used. In second condition, okay. In second condition we are using another three lambdas. Okay, another open that is 5, 6, 7. And third one is there 5, 6, 7. So then third one is 8, 9, 10. Okay, so different optical sorry defined type of circuit you have. Sorry, op-amp you are using. Okay, same type of op-amp but different man. Okay, now what happened? So here we are getting some triangular waveform from the circuit. Then that triangular waveform can be amplified. Okay, can be amplified by this op-amp. Okay, after amplification, so either back-to-back generators are given. Need not to get that negative voltage. That's why you have they are using that back-to-back generator. Okay, so then what happened? Here we can see inverting, okay, non-inverting amplifier. Okay, so that formula of non-inverting amplifier is RF by RI plus 1 within. Okay, so that's the basic gain. Okay, so we can multiply it and get the actual one. Okay, and finally we can see here the comparison normally happen. Okay, so you know that one port is connected to the resistance bank. So if you vary the port, automatically that vary the port, so automatically output can be changed. Okay, if output can be changed, means that port is represent for that first we are talking about, we are doing it for the open loop system. Okay, so if we change that port, okay, automatically that the amplitude of that signal can be increased. Okay, then you can use it. Okay, so by this way, and so DC value can be shifted. Okay, by this way. Okay, so triangular from you are getting, so that's amplification is there. Now you are comparing that amplified triangular with the DC value coming from the port. Okay, if you compare them directly, PWM is getting here. Okay, then through that PWM you can send that through that PWM you can send it to TP5 time. Okay, so by the basic thing, and what is the purpose of the diode? To minimizing the negative signal. Okay, so if you go for that, I hope you are able to understand what is there. So every values are given, what you need to do, everything is mentioned over there, and what type of diagram you need to fetch, that also given here. So for this is for non-isolated type. After the from this one, we are going to share for isolated type. Okay, so that features they have mentioned. Okay, what new kind of everything has been mentioned. Okay, features, what are the values. Okay, my previous value, it is matching with your previous value or not. So if it is not matching, so you can change it. Okay, directly you will get it from here. Okay, so after that what happened, you are comparing them. Okay, so after that you are comparing them, and for non-isolated what you are doing, you are using some non-isolated transformer Okay, otherwise, okay, you are using for for the 6 for the minimal, what it is good, but for more, so that we are using some uh, so I hope you are getting that points. Okay, so for now we can also use that optical opto isolator as well as isolation transformer. Both we can use. Okay, and based on that costing, so input side as well as output side, the processor, everything can be changed. But power circuit will be intact. So after that you can vary that resistance. So you can see how the frequency of that repeating sequence are changing. Vary this R4 resistance. Okay, if you want to change this resistance, so you can see how that PWM is varying. Okay, so both the thing you can understand. Okay, from here, so directly you can cross check it as it is right or wrong. So parameters values are given over here. Okay, directly you will get directly you can plot it. Okay, and you can understand that value. Okay, then so here you can see different value for changing of that R4 load. Okay, so if you change that load, so automatically that RC value has been changed and everything can be you know that some results can come from every iterations. Okay, and any doubt is there, so what kinds of doubt you have faced, try to solve it. Okay, if there is doubt, if you are not able to solve, so please let me know. Okay, these are the results. Okay, that content I am going to share you. Okay, so if you have any other doubt, please let me know. Do you receive that document? Hello? Hello?
Yes, sir.
Okay.